Alright, you have to deal with my voice a little bit here because they shoved the breathing tube down it not long ago, so it's a little scratchy, so hopefully you can understand me okay. I'm gonna kind of speed through this real quick, and I'm not gonna talk a whole lot, just for the sake of my voice, but I'm just gonna hit off some key points for you real quick. So this unit's on equilibrium, and essentially we are used to, at this point so far, dealing with single arrows for reactions. And most processes and reactions actually happen in two directions simultaneously. So here's a couple examples of reversible processes. Liquid water can turn into gaseous water, and then it can turn back from a gas into liquid. Salt can dissolve, and then if the water evaporates, the salt water solution will turn back into solid salt again. So these are just two examples of processes that are reversible. Here's another one involving hemoglobin in your lungs. Now, some reactions do actually go to completion, and we draw those with a single arrow. This is the dissociation of hydrochloric acid, and we will go over this later in the year, but this is not a reversible reaction, so we just use the one-way arrow that you're used to seeing. Most reactions do not go all the way to completion, so eventually they reach this dynamic state where the reaction is going forward and it's going backwards simultaneously at the same speed. For those reactions, we use this two-way arrow. Now this graph is showing you the molar concentration and the change in that over time. So looking at this, if we started off with 0 nitrogen dioxide, and we started off with only dinitrogen tetroxide right here, eventually as this reaction proceeds from reactants to products, the amount of our reactant is going to decrease, the amount of the product is going to increase. Eventually they reach this point where you can see that the concentrations level off and they're no longer changing, but you still have concentrations of both products and reactants simultaneously. It's still firing backwards and forwards at the same time, but the concentrations are staying consistent. These two lines right here will rarely level off in the exact same spot. Usually they'll be slightly different. So this graph is showing the rate of the reaction, and you can see that the reaction's going faster here in the formation of nitrogen dioxide until eventually the rate's going to slow down, and here these match because the rate of the forward and reverse reaction are going to be the same. I'm going to skip over some of these slides that you're capable of reading on your own. I hope that's okay. So when we write an expression for the equilibrium, we're going to write what's called the equilibrium expression, and we're going to have a constant here. And this is either going to be Kp or Kc. So you'll see here that it says Kec, whoops, sorry, Keq. Keq can either be the equilibrium constant for concentration, you'll see a C, or it can be the equilibrium constant for your partial pressures. In that case, you'll have a P here. To write this expression, you simply take these molar stoichiometric coefficients and you make these your exponents, and then you put the concentrations of your products and your reactants into these spots. Now the key thing here is you're going to do your products on the top in the numerator, and your reactants need to go into the bottom. So if you have if you have 4 moles of A, you would put a 4 right here, and then let's say it was 0.5 molar concentration for A, you would put 0.5 here. So let's take a look at one of these so you can see how it works. We're going to write the equilibrium expression for this reversible reaction. We do our products first in the numerator. We have two of those, so you do the concentration of nitrogen monoxide squared divided by the concentration of nitrogens and oxygen gases in the bottom. These are going to be multiplied by each other, and this is going to be squared, obviously, and then that will give you your Kc value. Now, a couple of key things. Solids are left out of the expression, and liquids are also left out of the expression. So if you look at both of these examples, here you have two solids. Totally ignore those for this expression. It would just be CO2 on top, and you have 1 mole of that, so to the power of 1, which you don't have to write, divided by the concentration of carbon monoxide on the bottom. Here, water is a product, so we're going to leave that out of the numerator. We're going to do the concentration of chlorine gas squared, all divided by the concentration of hydrochloric acid to the power of 4 times the concentration of oxygen. Leave liquids out. So do not include gases. Do not include liquids or solids. Include gases and aqueous species only. The same way works for Kp. This is going to be for pressures, but instead of putting concentrations, we're going to put their partial pressures measured in atmospheres. This gives you an explanation of what partial pressure is. Take a moment to read this slide, make sure you fully understand this. Now, this is a conversion between Kc and Kp. You can basically ignore this in your notes. You will not see this on the AP exam, but there is a way to convert from Kc to Kp. But I'm going to skip through these next. Through any problems that you have to use this, we're not going to do. So for this one right here, we want to find Kc for this reaction right here. So the first thing you're going to do is write your equilibrium expression. So go ahead if you want to and pause the video right quick and write out this equilibrium expression for this reaction. So here's your expression, the concentration of hydrobromic acid squared divided by the concentration of hydrogen times the concentration of bromine. Go back to the problem at hand and plug in your concentrations for each one of these. And you solve for Kc. This is a unitless answer. There are no units involved in this. And we'll talk more about why there's no unit for this later. Like I said, we're going to skip converting between Kp and Kc. So, what's the point of finding Keq, either Kc or Kp? The value basically tells you if you have more products or more reactants. So it's going to tell us if this reaction favors the product side or if it favors the reactant side. So since your products are on top, if it favors products, it's going to be a big number divided by a small number, which is going to give you a large number. If it favors the reactants, you would have a small number on top divided by a big number, which would give you a decimal or a really small number. So in this example, our Kp is 0.0184. So this tells you that your number here on the bottom is larger than your top number in your fraction, which means that at equilibrium, you have more reactants than you have products. If your K value is large, as it is here, this tells you that we have more nitrogen and oxygen gas equilibrium than we have nitrogen monoxide gas. So this reaction has proceeded more towards products than towards the reactants. This kind of summarizes that. If your K value gets big, especially more than 10, the equilibrium lays far to the right. It's going to be mostly products. If it's less than 0.1, it's going to greatly favor reactants and the equilibrium lies far to the left. If your Keq is pretty close to 1, that means we basically have equal amounts of products and reactants at equilibrium. Take a moment to read this problem. So looking at this, do you have mostly AB or mostly A and B at equilibrium here? If you look, you have 1, 2, 3, 4, about 16 particles of AB, and you have fewer particles of A and B by themselves, which means that equilibrium, it favors reactants, so your K value is less than 1. Alright, so calculating equilibrium partial pressures, we have a problem where we start off with only water. So we only have water, and it's water vapor. It's in a rigid container, and its initial partial pressure is at 0.784 atm. What are the partial pressures at equilibrium? So here, you can see that you're given your K value. So the first thing that we're going to do is set up something called the ice table. This is the most important part of this lecture right now. We're going to use ice tables for the rest of the year, so make sure that you understand how to use them. So basically, ice stands for initial change equilibrium, and you're going to write your initial partial pressures up at the top. So start off by writing your reaction, draw your ice table. It told us we started off with only water. That means our partial pressure of these two is going to be 0 because we don't have any yet, and it's at 0.784 atmospheres. Now, as this reaction proceeds from reactants to products, we're going to lose some of our water, and we're going to gain hydrogen and oxygen gas. So this is going to decrease by an amount that we don't know yet, so we're going to call that X. But there's 2 moles of it, so we're going to call that 2X. This is going to increase by some amount, which is going to be equal to this. So we're going to call this an increase in 2X and this in X. So basically, whenever you set up these ice tables, your reactants, you're going to do plus, and your products that you make, you're going to add X or 2X or 3X. Whatever this coefficient is here is always going to go in front of your X. So in this case, these both have a 2 coefficient. This has 1. Then you subtract anything from your reactants and you add for your products. So at equilibrium, this partial pressure is going to go down, and this is going to go up by the same amount, and this is going to go up by half that amount, only X. Now what we're going to do is we're going to write our equilibrium expression that we learned how to do, but we're going to substitute these values in for it and set it equal to our K value right here. So this is our equilibrium expression. Partial pressure of hydrogen squared because of the 2. Partial pressure of oxygen divided by the partial pressure of water squared because of the 2. Take your values from your ice table at equilibrium, and this will be 2X, this will be X, and this will be what? 0.784 minus 2X. Now, on the AP exam, luckily they don't make you use the quadratic equation. So if you think about this real quick, our K value on this problem is very, very small. Look how small this number is, times 10 to the negative 42. That means this greatly favors reactants. You're going to make very little hydrogen, oxygen gas. Okay, and this should make sense because here you're looking at water. So think about water as it exists in nature. A very small percentage of it actually breaks down to hydrogen and oxygen gas. Because we have such a small value here, this change is going to be so small here. This is going to be such a small, tiny number that we can essentially ignore it. And we can just rewrite this as 2x squared times x, which would be 2 squared is 4, and x squared times x is x cubed, divided by, pretend like this doesn't even exist right here, and just do 0.784 squared. This was given to you in the problem, and now you can solve for x by multiplying both sides, divide by 4, and take the cube root. And you get that x equals 7 Sorry, 6.7 times 10 to the negative 15 atmospheres. That's going to be the partial pressure of oxygen in equilibrium, which is our X value right here. We have 2 moles of hydrogen gas at equilibrium, so the partial pressure of this equilibrium is going to be twice as much. Since this value is so small, remember we can ignore it, so we just say that the partial pressure equilibrium for water is still going to be 0.784. So this is the final answer. The partial pressure for this. Partial pressure for this is twice as much. This is relatively unchanged. And you can check this by plugging this back into your equilibrium expression, and it should equal the value that was given to you in the problem. All right, let's do another one. Here we want to find Kc. This has to do with concentrations, not partial pressures, because of the C here. So we have to convert this to a concentration. This is simple. We were given moles of our reactant, and we were given the volume, so we can very easily find out the molar concentration by taking our moles and dividing it by the volume. We're given the Kc value, so once again we're going to write our equilibrium expression. So we have 0.194 moles of COCl2, which is a substance called phosgene, and we'll get more of what this is later. But the problem told us we only started off with phosgene. We don't have anything else there. COCl2, that's all we have. We have not made any CO, carbon monoxide, or any chlorine gas yet. We only have reactants. So we set up our ice table. Once again, this is our molar concentration of our reactant. We have no products at the moment. Our coefficients for each one of these is 1 in this reaction. 1, 1, and 1. So this is going to go down by X. We're going to lose some of this, and this is going to go up by X, and this is going to go up by X. So at equilibrium, we're going to have 3.3 times 10 to the negative 2 minus X. We're going to have X, and we're going to have X, because 0 plus X is X. We're going to plug this into our equilibrium expression. Once again, products over reactants. And we get something like this. So, once again, just ignore the X, because the change is going to be very, very small. And you end up with X squared. By simplifying this, over 3.3 times 10 to the negative 2 is equal to this value, which, don't forget, that was given to you in the problem. Now you simply solve for X, and once again, you need to write out that the concentration of carbon monoxide and chlorine are both going to be 4.9 times 10 to the negative 20 molar, and the concentration of phosgene is going to be 3.3 times 10 to the negative 2 molar. And you can check that out and make sure that it equals this. This just shows you an application of this. It was used in World War II to produce chlorine gas, and this basically reacts with water in your lungs to form hydrochloric acid, and it kills people in a very, very terrible way.